p76, I'm going to talk about comparison of series, specifically the direct comparison test. Right? So, and we'll get into what some of this terminology means, but I'll just read the rules first. If the series b sub n going from 1 to infinity converges and a sub n is between 0 and b sub n, then it would make sense that a sub n, if it's very much like the sandwich theorem or the squeeze theorem, that this would also converge, because if the b sub n is converging, it would make sense that it's gonna trap the a sub n between itself and 0 in some capacity. A sub n is not going to break free from the bounds created by 0 and b sub n. Then it may not converge to the same numbers like the squeeze theorem would, but it's going to converge to something, otherwise it would break the bounds of 0 and b sub n. So a sub n ought to converge. All right. So I'll give you a quick sketch of that using, let f of x represent, and actually let me move this up a little bit, the path generated by a sub n, and g of x represent the path generated by b sub n. Okay? And so what I'm saying, actually what this rule is saying, is that if you know that b sub n, well, maybe this wild function for low values is eventually going to converge onto something. I don't know why I kind of got a little wiggle there at the end. And you have 0. So this is g of x. A sub n can behave any way it wants as long as it's always in between g of x and 0 for the relevant values of n, which is greater than or equal to 0. So it doesn't matter what's happening down here. It could go down, it could go back up. A lot of different possibilities. We don't care about any of that. We only care about values greater than or equal to 0. Let me just move that over because it got a little on the wild side there. We don't know where a sub n is going to go, but we do know it has to converge onto something. All right. Just cleaning this up a smidge more. All right. B sub n we define as what we call the parent and behavior model of a sub n. Or that's actually something I call the parent EBM. I've never seen anybody else call it that, so I don't know. Maybe try Googling it. Maybe I subconsciously stole it from somebody else, but I'm pretty sure. I was like, oh, what should we call this? And I thought parent EBM sounded good. Anyway, it was years ago, so by now the secret might be out anyway. So that's my plausible deniability. If a sub n diverges and a sub n is between 0 and b sub n, then b sub n must also diverge. The idea being, so same general structure here. I'll actually largely use the same diagram. That, well, actually, let me hang on to the g of x. If we can't, sort of like you can't control the function that's trapped in between the other two. So it's saying, well, I got this f of x, and it just refuses to converge onto anything. If I know that g of x always has to be larger, because f of x is in between g of x and 0, there could never be an instance where they cross. So this would always have to stay on the high side of f of x. So where f of x goes, g of x would follow. All right, so if f of x, which represents a sub n, diverges, and so would b sub n. All right, so the examples determine whether the following converge or diverge. Well, let's start off by finding the parent EBM. All right, so we know the a sub n, that's given. That's ultimately what we're trying to find, quote unquote, the answer to. But let's discuss the parent EBM. The end behavior model associated with the a sub n. All right, so the way we find an EBM, we talked about this before, is we take the term with the highest power on the top of the fraction and divide it by the term with the highest power on the bottom of the fraction. The parent part of it is just saying to strip away all the trimmings. You know, for example, y equals 2x squared plus 3x plus 2. It's a given function, right? Given equation. The parent, or well, the parent model, parent function, would just be y equals x squared, right? Where you strip away all the trimmings, everything except for the thing that defines it as a quadratic. So that's what's happening here. If there's any coefficients or any additional values with lower powers that are added on, we would strip those away. All right? So that's what we're going to call b sub n. So we want to look at this and see if we can make a determination of what's happening with b sub n under the same conditions. Okay, so we're going to find the sum from n equals 1 to infinity of b sub n, which is the sum from n equals 1 to infinity of 1 over n to the third. Now this is a p-series. All right? And specifically, a p-series where the p-value is greater than 1. So b sub n, you know, the sum, as n equals 1 to infinity, converges. All right? So b sub n captures, in between itself and 0, a sub n. So we need to establish that relationship. All right? So if we use the function notation, let f of x be equal to 1 over x cubed plus 1, and let g of x be equal to 1 over x cubed, we need to establish that g of x is greater than f of x for all relevant values of x, greater than or equal. All right, calculator. Oh, I already have part of it in. You know what, I'm going to retype because I want to have the f of x come first. So alpha y equals 1 over, would be x to the third plus 1, and then 1 over alpha y equals, so 1 over just a plain old x to the third. All right, make one bold so it stands out. All right, now numerically you can verify this just in your mind, because the 1 is being divided by a larger number here in all cases than it would be over here. So this fraction would necessarily have to be smaller than this one. So you have that relationship, but we could also look at it visually. And it's kind of ugly, but if we bring it in, you know, it's all about the appropriate window. We'll go from 0 to 10, 0 to 2, I guess. It looks like the bold is above the not bold, but if I really want to bring it in, let's make it like 0.5. It looks like it's still above. Let's make it like 0.05. Almost indistinguishable. But you can go into the table and look, you know, 128th, 127th, 126th, you know, you get the idea. All right, so this is a true sentence, so yes. All right, so that tells me that based off of all these conditions, and it's all about the conditions, you can't just say on a test, I'll tell you right now, you can't just, unless it's multiple choice, that's a different story, but If it's anything that requires you to show work or an explanation, if you just say converges or diverges, you will not receive any credit, right? Because that is nothing more than just guessing, right? And I don't give credit for people guessing the right answer, all right? Like I said, unless it's multiple choice, in which case, that's one of the reasons why those are there. Gives you that, like I thought I knew how to do this, but let's let the fates decide, right? So, therefore, this converges by the direct comparison test. All right. If you write this, but you don't have any of this stuff, you haven't done your job. All right. Keep that in mind, please. Very important. Same idea for number or part B. We have an a sub n. We need a parent of that. All right. The parent EBM. All right. Well, the parent function to this n behavior model. Again, there's no extra coefficients and stuff flying around, so b sub n is going to be 1 over 3 to the nth. All right, so I need the sum, and really, I'm going to start stealing some work here. So 1 over 3 to the nth. Now I'm going to clean that up just a smidge, because I could rewrite this as, let me bring it in, the sum from n equals 1 to infinity of 1/3 to the nth. And if you throw in front an assumed 1, now you have a geometric series. All right. So this is going to converge. So this is b sub n converges by the geometric series test, and that's because the r value is less than 1. All right. Well, really between 0 and 1, but less than 1 is fine. You get the idea at that point. It's really the absolute value, but I don't think I'm lying when I say that I've never taken off credit if somebody wrote r is less than 1, because I know what you're talking about. Slash, I just did the same thing. So there's that. Now we have to verify that the parent and behavior model, now that it converges, the parent and behavior, that it is in all cases, all relevant cases, larger than the given. So let f of x be equal to 1 over 3 to the nth plus 2, and let g of x be equal to 1 over 3 to the nth. Again, the question is, g of x bigger than f of x? We go to our calculators and verify. I don't often make trick questions, but some problems, they just end up being tricky, because you kind of look at it and think that it's a direct comparison test, for example, and it's something else, and usually is something else because you didn't verify the conditions. All right, so here's an example of that. 3 to the x. Again, I want to make sure my y2 is larger in all cases than y1, all relevant cases. All right, kind of looks the same idea. I mean, if you want to play around with the window, you could, but I can go, a little further out actually, just to show that relationship, and then go into the table and just verify that in all cases, and again, relevant cases, so greater than or equal to 0, the values, they look like they're the same, but you can see they're ever so slightly different. All right, well, okay, that's not a good example. They're ever so slightly different. Okay, so what we would say here again is that the series converges by the direct comparison test. So you can see that we're using multiple tests in the same problem. Right. So the direct comparison test is not a test in and of itself. It relies on other tests to act in a supporting role. All right, and so the last one, parent EBM. So that's going to be b sub n is equal to 1 over radical n, but I'm going to write that as 1 over n to the 1/2 power. Make it a little friendlier like. All right. So again, just stealing some of the notation here. Actually, I can steal a lot of this because it does have a p series look to it. All right, except the power is 1/2, and we know, hopefully, but that's the kind of thing where it's a fallacy of it, teacher mentality, is that I teach you something and the hope is that you've mastered it immediately. Maybe you don't know it just yet, but you will. Any p value that's less than or equal to 1 but greater than 0 is going to cause it to diverge. Oh, I don't need the n there. Dinverge? No, diverge. All right, so we have a divergent situation. Okay, so very important here to remember that we're not always looking for the same relationship between f and g. So I have, again, let f of x equal 1 over the square root of n minus square root of x minus 1, and g of x equal to 1 over the square root of x. But now I want the relationship to be the reverse. I want g of x to be less than or equal to f of x, because I want, if the g of x, which corresponds to the parent EBM, which diverges, if that's below the f of x, then f of x will never be able to converge onto numerical value, because if g of x is too busy going on its merry way to infinity, and g of x is always above f of x, then it'll necessarily have to go on to infinity as well. All right, so 1 over, yes, alpha y equals 1 over the square root of x minus a 1. I think I typed it in correctly. And then 1 over the square root of x, alpha y equals 1 over the square root of x. And then I'm just going to make sure again that this one's bolded. Start off with a zoom 6. All right, so the bolded one, which we know diverges, even though it doesn't really look like it here, it's going to diverge. It appears to be trapped between the non-bolded and 0. All right, so let's just get a closer look. For x min, 0 is fine. For y min, 0 is fine. We don't need to go too big. Let's make that a 5. All right, so it seems to be leveling off in terms of the sequence. All right. But in terms of the summation, unless this settles in onto something, I mean, it appears to be asymptotic, it's always going to be increasing in value. All right. So it gives us a sense. I mean, we knew that the functions would maintain that relationship one in between the other, but there also is never an instance where this is leveling off to a point where it would give a finite sum, right? So if you really want to get a look at the divergent nature of it, then you got to switch over to parametric mode and pop in. I mean, really, you just need the original. I mean, you can put in, if you really want to get a close look at it, you can put in the parent EBM also as a new one. as a new function, but I think we'll get the point just by looking at this one. So second graph. Let me get back to table set 0, 1. That is errors all the way. Okay. Oh, starting at 4. Well, even starting at 4. Oh, somehow I missed that along the way. I mean, it ends up not mattering, but that's kind of an issue. All right, so just making sure I typed it in correctly. So we're getting a nice juicy error here. So that's telling me that the calculator is either having a hard time with it, or there's something numerically that it just doesn't like. I'm thinking the calculator's having a hard time with it. If you want to get the actual set of sequence values, then you go into the sequence mode and just type in, alpha y equals 1 over square root of n minus 1, but like I said, we want to start this off at 4. And then you can see the sequence values. But this is only going to confirm what we already knew from the function mode. It's unfortunate that the calculator kind of let us down with the parametric one, which gives us the partial sums. But while I'm here, let me make the corrections here. This should be a set of 4s. The relationship is still true. All right. And so, yes, this size relationship is the case. And so we would say the sum from n equals 4 to infinity of 1 over the square root of n minus 1 diverges by the direct comparison test. All right. Now, just a word on that whole bottom number thing. If we wanted to, and some people feel an absolutely pressing need to do this, it's hardly ever necessary, as long as the lower bound is something finite, which is always the case. You could redefine your summation so that your lower bound is equal to 1. All right. So the way you would handle this is by listing out the first few terms of the sequence. All right. So we're already in this mode, so maybe we'll just take a look at that real quick. All right, so 4 gives you a 1, and then the 0.809. All right, and so all you'd have to do is come up with a new expression in the radical that would lead you to this result. So, while I'm here, I might as well. So 1 over, it would be 2 minus 1, so 1. Well, let me just write it this way. Plus 1 over, the next one is it's gonna be a radical, but it's fine. You plug in, so we plugged in the 4 already, so the next one could be radical 5 plus 1 over radical 6 plus 1 over radical 7, all minus 1, and so on. All right, so if I wanted to rewrite this, and even, going back, I'm just going to write this as a radical 4. If I wanted to rewrite this so that my lower bound of the summation is equal to a 1, then I would just need a new way of saying or giving that radicand of 1. All right, so this would stay put, this would stay put. I would have to be thinking, okay, so if I want to get to a 4 here, I think I said 1, if I want to get to a 4 using that lower bound of 1, what would it have to be? To get from a 1 to a 4, I could do it 2 ways. I can multiply by 4, which is not going to be helpful, because if I put in a 2 times 4, it's going to give me 8. That's not a 5. Or I can add 3. So I could say n plus 3 If I plug in a 1, I get a 4. If I plug in a 2, I get a 5. If I plug in a 3, I get a 6, and so on. So we'll get the same series with a different looking expression. Now, if you look at this carefully, you see that it has the same general structure as what we were dealing with before. All right. So then if I were going for a parent EBM, what I would do is exactly the same thing, because I would take the 1 over the radical n plus 3. All right, so for my 1 over radical n plus 3, like I said, we strip down anything that's not part of the parent function, we'd still get the 1 over n. So instead of comparing 1 over n plus 3 to the original function, I would compare 1 over n plus 3, radical n plus 3 minus 1 to the 1 over radical x. All right, so I can just put that in really quickly. All right, so that would be the original graph to compare against the parent EBM. Looking at the picture, same general idea. All right, so as long as the well, actually, in this case, it looks like maybe it's not, but if you look at it carefully, you'll see that it is. I'm just going to bring it in really quickly because I don't want to get to a point where I'm disproving myself. Yeah, it's after 1 that it transitions to be belonging. But at first, it was very scary. It looked like it was actually greater, right? But crisis averted. So it still follows the same path, and it would still cause a divergence, and it would still be by the comparison test, right? Direct comparison test.